Hello, my name is Putu Arindra, and here I will discuss the material of testing and inspection of metals, the quest for quality, with the main reference from the book Metallurgy for the Non-Metallurgy. Okay, 7.1 Metallography. Metallography is the scientific discipline of examining and determining the constitution and the underlying structure of the constituent in metal and alloy. The examination of structure may be done over a wide range of length scales or magnification levels, ranging from a visual or low magnification examination to magnification over 1 million times with electron microscope. Metallography may also include the examination of crystal structure by techniques such as X-ray diffraction. Some story. The critical factor is the light microscopy of metal is the surface preparation of the specimen. This is the basic insight made by the father of metallography, Henry Clifton Sorbet. This application of microscopy occurred more than 2 centuries later than the initial application of the biological microscope, because the microscopy of metals requires careful preparation of the surface. Unlike biological samples, metals are opaque and thus require reflect like microscopy. In contrast, biological samples are transparent and can be examined by transmit light. Sorbet understood the need for proper surface preparation when examining metals by reflect light microscopy. The first step is careful polishing of the specimen. The other piece of metallographic puzzle is the art of etching. An extremely smooth surface appears nearly featureless when examined by reflect light microscopy, because the light reflects uniformly from the surface and appears as a uniform contrast to the human eye. The special techniques are required to change contrast difference between the different pairs of constituents. This method includes etching, thin film formation, or special illumination models with light microscope. Of the various contrasting techniques, chemical recipe for etching the surface are the oldest. Etching even precise, surveyed by at least 4 centuries, as in the case of macro etching technique to reveal the mass pattern of sword and various pieces of armor. Macro etching was also used to reveal the structure of polishing meteorites, such as the famous white Manhattan structure discovered in 1808 by Count Alois von White Manhattan, a geologist and museum curator in Vienna, and his co-worker Carl von Cherebis. There is various meteorites, and through the effort, revealed the outstanding crystalline pattern in the Ilbogon iron meteorite that fell in 1751. An excellent example of their work. This type of structure, which appears in many alloys, is now referred to as a white Manhattan structure. From this beginning, the importance of specimen preparation remains central today. Many deficiencies arise when proper preparation methods are bypassed. False structure can arise from the preparation in many ways. In particular, Jose Ramos Villa was the first to realize that artifacts were sometimes being observed due to the presence of a layer of distorted or disturbed metals formed during the early stage of surface preparation and not during polishing itself. He demonstrated that the true microstructure was seen only when the disturbed layer was removed, and he devised a method from doing this, the application of alternate etching and polishing steps. Metallography in quality controls produce in full several steps of sample selection and specimen preparation. The number of samples to be examined is usually specified for different stages of production. These procedures generally also specify the area of interest to be examined, because the structure of materials can be greatly altered by the generation of heat and by plastic deformation. Considerable care must be taken in sectioning or cutting samples, especially when abrasive cut-off wheels are used. 7.2 Harness testing. Harness, as the term in use in industry, may be defined as the ability of the material to resist permanent indentation of deformation when in contrast with an indenter under load. Generally, a harness test consists of pressing an indenter of no geometry and mechanical property into the test material. The hardness of the material is quantified using one of variety of scale that directly or indirectly indicates the contrast pressure involved in deforming the test surface. Because the indenter is pressed into the material during testing, hardness is also viewed as the ability of a material to resist comprehensive loads. The indenter may be spherical, pyramidal, or conical in the Brinell figures. And knob test, the hardness value is the load support by the unit area of the indentation, expressed in kilogram force per square millimeter. In the Rockwell test, the depth of indentation at the pressurized load is determined and converted to the hardness number, which is inversely related to the depth. Hardness, though apparently simple in concept, is a property that represents an effect of complex elastic and plastic stress field setup in the material being tested. The microscopic events such as dislocation, movement, and phase transformation that may occur in a material under the indenter should not be expected to exactly repeat themselves for every indentation, even under identical test conditions. Yet experience has shown that the indentation produced under the same test conditions are macroscopically nearly identical, and measurement of their dimension yield fairly repeatable hardness number of a given material. This observation by James Brinell in the case of spherical indenter led to the introduction of the Brinell hardness test. This was followed by the other tests mentioned previously, each with its own unique advantage over the Brinell indenter. Hardness tests are no longer limited to metals, and the tools and procedures currently available cover a vast range of material including polymers, elastometers, thin film, semiconductor, and ceramic. Hardness measurement as applied to specific class of materials convey different fundamental aspects of those materials. Hardness testing is perhaps the simplest and the least expensive method of mechanically characterizing a material because it does not require elaborate specimen preparation, involves rather inexpensive testing equipment, and is relatively quick. There are some fairly occurred quantitative relationship between hardness value and other mechanical property of materials such as ultimate tensile strength and strain hardening coefficient. Hardness testing is also of one of the few non-destructive tests available to qualify and release finished components for use in the indented application. Microhardness testing. In microhardness testing, loads are less than 1 kg and indentation can be seized only with the aid of a microscope. Knob and Vickers tests are in this category. The Vickers indenter is a square-based diamond pyramid. The applied load force is generally 1 kg or less. A typical impression also is shown. The specimen must have a polished metallographic surface for viewing and measuring with a microscope at a magnification of approximately 200 to 400 times. The specimen is replaced in a fixture and the microscope is focused on the area of interest. As in other hardness testing, the higher the number, the harder the material. The microhardness test can be used to assess the hardness of constituent observed in a macrostructure from the area of the indentation. Knob denter. The tester and operation procedure for testing are the same as those for the Vickers test. Differences are in the geometry of the indenter and calculation of area. The knob indenter is a rhombus-based diamond pyramid that provides an impression of the shape. Only the long diagonal measure, because the knob impression has one short diagonal. It can be used to advantage where impression must be made close together, as in the measurement of case depth. So the knob impression often preferred when specimens are very thin. The depth of a knob identification is only half of the Vickers identification. Nanohardness testing. Nanohardness tests depth on the simulation measurement of the load and depth of indentation produced by those loads. It has become a primary tool for examining these film coatings and material with surface modified by techniques such as ion implantation and laser heat treatment. Measuring hardness in the films and coating is more difficult than performing similar measurement on monolithic material because the load displacement data acquired from nanohardness testing depend in complex ways on the properties of the film and the substrate of which it resides. Thus, obtaining absolute measurement of film properties is often difficult and requires careful data analysis. Under certain circumstances, the machine compliance itself can contribute significantly to the total measurement displacement under load. So the instrument used for performing this measurement must be carefully calibrated and its contribution removed from the load displacement data in a manner analogous to tension and compression testing. Hardness convention. Because testing labs are often limited to the types of equipment they have available, this limits the types of testing that they can perform. For this reason, it is often necessary to take the reading acquired in one hardness test and convert it into a value that will be obtained in different types of hardness tests. Because all of the tests in common use today are not based on the same type measurement, it is not surprising that universally recognized and accepted hardness conversion relationships have not been developed. Hardness conversion instead are based on empirical relationships that are defined by conversion table limited to specific categories of material. There is different conversion tables are required for material with greatly different elastic module or with different strength hardening capacities. 7.3 Tensile testing. The conventional measurement of ductility that are obtained from the tension test are the engineered strength at fracture F and the reduction in area RA at fracture elongation and reduce in area usually are expressed as percentage. Both of these properties are obtained after fracture by putting the specimen back together and taking measurement of the final length and using the diameter measurement at fracture to calculate the final specimen's cross-sectional area. Testing machine. Mechanical testing machines have been commercially available since the late 1880s and have evolved from purely mechanical machines such as the popular Little Giant hard crank tensile tester of Tinius Olsen, circa. Today, the sophisticated machine with either electromechanical or servo-hydraulic drive provide rapid and precise measurement of load and displacement. These values can then be used to calculate properties such as ultimate tensile stress and elongation, yield stress, modulus of elasticity, and other mechanical properties. Conventional testing machines for measuring mechanical properties include tension tester, compression tester, or the more versatile universal testing machine. Universal testing machine have the capability to test in tension, compression, or bending. The word universal refers to the variety of stress states that can be studied. Universal testing machine can load material with a single continuous pulse or in a cyclic manner. Other conventional testing machine may be limited to either tensile loading or convergent loading, but not both. These machines have less versatility than UTM equipment, but are less expensive to purchase and maintain. 7.4 Fracture toughness. Fracture toughness testing. With the advent of linear elastic fracture machine, engineers now realize that the design of structure and machines can no longer under a condition be based on the elastic limit or yield stress of a material. Various tests have been developed to measure the fracture toughness of material, and these tests are generally conducted on the specimen containing a sharp, persisting crack. 5 different standard specimen geometry are specified in ASTM E399, but most fracture toughness tests are conducted with either the S-notch band or compact test specimen. Testing is normally conducted on the screwdriver or servo-hydraulic machine that loads the specimen at a pressible rate, and the measurement of load and displacement are taken during the test. The resulting data are subjected to the analysis produced to evaluate the desired toughness parameters. These toughness results are subject to qualification procedures to see if they meet the conditional for which the toughness parameters are accepted. A factor of considered in this type of testing is microstructural anisotropy. Material anisotropy is a term used to describe the dependence of material properties, such as fracture toughness, yield stress, and elastic modules on the texture observed in the microstructure. When a material has mechanical properties that are independent of direction, it is said to be isotropic. Conversely, if the material has mechanical properties that depend on a particular orientation, it is said to be anisotropic. Anisotropy may be resolved from the methods of reduction that were used in processing the material during manufacturing. Material forming process, such as drawing, extruding, rolling, or forging, can greatly affect the microstructure and texture of the material. For example, rolling operation tend to deform material primarily in one direction, the rolling direction. Examination of the microstructure of a steel specimen that has been deformed by significant rolling reduction often reveals carbides oriented along the rolling direction. Additionally, the fracture toughness of a material is affected by the microstructural and mechanical change a material undergoes. Through processing such as heat treating, to provide a common schemes for describing material anisotropy, ASTM standardized the following 6 orientations: LS, LT, SL, ST, TL, and TS. In design for fracture toughness, consideration of anisotropy is very important because different orientation can result in widely different fracture toughness value. When the crack plane is parallel to the rolling direction, the great impurities and intermetallics that lie in these planets represent is easily fractured perhaps, and the toughness is relatively low. When the crack plane is perpendicular to these weak planes, decohesion and crack tip blunting or stress reduction can occur, effectively toughening the material. On the other hand, when the crack plane is parallel to the planes of the defect, toughness is reduced because the crack can propagate relatively easily. 7.5 Impact testing. In an impact test, the specimen is subject to the dynamic shock loading to elevate the response of a material to rapid change in loading, such as that experienced by an axle shaft when a car hits the crack hole. When a specimen is placed in the path of swinging pendulum, the pendulum must be end or fractured the specimen if it is to continue its arch. The amount of energy required to break the specimen is absorbed by the pendulum, which reduces the height to which the pendulum rises. The difference between the height to which the pendulum can rise unimpeded height and the height to which the pendulum rises after breaking the specimens represent the energy absorbed in the breaking the specimen. This energy, expressed in Newton meters or foot-pounds, is called the impact energy of a material being tested. The two most common impact tests are Crappie and Isert test. The Crappie test often is done on specimen of a range temperature because some materials may exhibit a ductile to brittle tension at low temperatures. For example, and only small amount of energy is needed to fracture low carbon steel specimen at lower temperatures. 7.6 Fatigue testing. Parts subject to reference cyclic stress of tensile in surface even though the applied stress may be well below the yield stress of the material. This applied stress may cycle between tension and compression, or between a minimum and a maximum value of tension stress. In addition, the magnitude of the tensile stress may vary over time. Fatigue is the progressive, localized, and permanent structural damage that occurs when a material is subject to cyclic or fluctuating strains at nominal stress that have maximum value less than the static yield strength of the material. In general, three simulation conditions are required for the occurrence of fatigue damage: cyclic stress, tensile stress, and plastic strains. If any one of these three conditions is not present, a fatigue crack will not initiate and propagate. The plastic strains resulting from the application of cyclic strains initiate the crack, and the tensile stress promotes crack propagation. In general, fatigue normally consists of a crack initiation phase followed by a crack propagation phase. This separation of the fatigue process into initiation of propagation phase has been an important observation in the transfer of the multi-stage fatigue process from the field to the laboratory. Three types of fatigue testing methodologies are commonly used. The one high cycle stress control by fatigue testing, low cycle stress control fatigue testing, and fatigue crack growth rates testing based on the fracture mechanics concept of stress intensity K at the crack tip. 7.7 Non-destructive testing. Various non-destructive testing, or NDT, and inspection techniques are commonly used to detect and evaluate flaws or defects in engineering systems. Of the many different NDT techniques used in industry, liquid penetrant and magnetic particle testing account for about one-half of all NDT. Ultrasonic inspection methods and X-ray methods account for about another third. Eddy current testing about 10%, and all other methods total only about 2%. They do the represents. However, the most commonly employed methods in additional ultraflow detection is usually considered to be the most important aspect of NDT. There are also several other important application areas. These include leak detection, metrology, structure or microstructure characterization, stress or strain response determination, and rapid identification of metals and alloy. Liquid penetrant inspection is non-destructive method used to find discontinuities that are open to the surface of solids, essentially non-porous material. The liquid penetrant inspection process discontinually open to the surface of a metal is located by allowing a penetrating dye or fluorescent liquid to infiltrate it. Excess penetrant is removed in the next step by various means such as wiping with a cloth or by washing directly the water, treating with the emulsifier and rinsing, or removing with a solvent. This is followed by applying a developing agent. This agent causes the penetrant to seep back out discontinually and register as an identification. A color dye or a fluorescence compound is usually added to the penetrant liquid. Depending on the amount of penetrant that ships to the developer, the crack width can appear up to 100 times larger than the actual size. The equipment required for liquid penetrant inspection is usually simpler and less expensive than the use for more other NDT methods. The inspection can be performed at many different stages in the production of a component, as well as after the component is placed in service. Relatively little specialized training is required to perform the inspection. However, only imperfections upon the surface can be detected, and rough or poor surfaces are likely to produce false indications or flaws, as well as flaw orientation can be found regardless of the size, configuration, internal structure, and chemical composition of the workpiece being inspected. Liquid penetrators can slip under various types of minute surface opening by capillary action. Therefore, the process is well suited to detect all types of surface crack, lab porosity, and shrink edge areas, lamination, and similar discontinuities. It is used to extensively to inspect ferrous and non-ferrous metal work and cast product, powder metallurgy parts, ceramic, plastic, and glass objects. This method cannot never fail to identify crack or flaw in ferrous parts if the defects are filled with the materials such as scale that can be produced during atmosphere annealing operations that are excused prior to inspection. In order for the crack to be detectable by these methods, it must be able to draw the liquid in, and the presence of scale on other material in the crack can prevent this from happening. Okay, that's all about the testing and inspection of metal, the quest for quality. If you have a question, you can write below in the comment section. That's all from me. Thank you.